So now, if we want to understand how to, for example, rewrite the pressure in terms of the singular behavior of the singular molecules, right? We need to use some statistical tools, which just means that we need to define some quantities that are useful for us. For example, let's say that we have many particles, right? And not only one that is going in the x direction. Well, then at this point, it becomes useful to define an average Vx square velocity. How do we do that? Well, I will just sum up Vx for particle 1 squared plus Vx for particle 2 squared plus ... plus I have even an nth particle, right, in the n direction. Here I inverted the index, but it's the same, okay? And then since I need to create an average, I will divide this by the number n, which is the total amount of particles, right? So the total particles. Yes. So what is the total force now that it's gonna act on the wall, on one of the walls, right? Well, this is going to be, for example, F in the x direction. It's going to be m divided by L, which are constant, so I'm just going to keep them. And then it's going to be Vx1 squared plus Vx2 squared plus ... plus x squared. Okay? And this means that I can rewrite this as m divided by L times what? Times actually n times Vx mean bar squared, right? So I can rewrite these that I have in parentheses using this expression that I found over here as n times the average velocity in the x direction squared. I can do much more than this. I can go into 3D. It means that instead of considering just speeds that are in the x direction, I can consider speeds that are actually in the x, y, and z direction. And therefore, I could define a speed v as the square root of vx squared plus vy squared plus vz squared. And this I'm just doing it with Pythagoras, okay? Pythagoras extended to 3 dimensions. But therefore, if I can define v in this way, well, then it means that I can also go and define what is the v average squared, which is just going to be vx average squared plus vy average squared plus vz average squared. Now, I have to assume, or let's say I have to work in some condition here. So somehow I have to assume that on average, these 3 average speeds, they are going to be actually the same. So if I have a lot of particle, I can actually work in the assumption. And it's not totally an assumption because on average, this is really true if you have an enormous amount of molecules moving, that the average of the speed in one direction square, it's actually the same in all the 3 directions, okay? So this means actually that this v that I wrote over here, it's actually 3 times, for example, vx bar squared. So it means just that vx bar squared, it's actually a third of the average speed squared. And this helped me a lot because now I can write that F in general, so not only in the x direction, but a general force acting on the wall, it's going to be a third times V bar. I'm using exactly this last result here, okay? So I'm using the fact that I know now this times what? Well, times m divided by L times n. All right? Now, what is the pressure? Well, the pressure is defined as a force per unit area. And therefore now, since the area is L squared, I can just divide this force by L squared. So let me write it here. So I have a third V bar squared M times N. But then now I have, oh sorry, I forgot an L here, right? Yes, so this means that actually this can be written as a third V bar squared M over L cubed times N. But actually what I'm writing now, it's basically the volume in the denominator. So I have a third V bar squared M times N divided by the volume. But what is actually the mass divided by a volume? Here. Well, the mass divided by the volume is the density, right? A density that I indicate with the Greek letter rho. And actually, it's not really only m divided by b, because m in this case, it's the mass of one particle. So if I sum all the masses, so I multiply m by the number of molecules, I really have the density of the gas, okay? So the density in this case is just going to be m times n divided by the volume, right? So actually, I'm finding out that the pressure can be expressed as a third of V bar squared times the density, which is a great result now, because it means that the pressure depends on the square of the average speed, but also on how many particles I have per cubic meter. And this makes sense, right? The more particles I have, the larger it's going to be the pressure. Yes.